In the previous video we looked at collisions as an example of where conservation of momentum is important. We're going to have a look at another example in this video, then I'll leave you with a few others to have a think about as well. So this is basically to show that this idea of conservation of momentum, it's not just an idea that is interesting, it's actually useful in designing systems and in this case getting rockets to fly. So with rocket propulsion, it's underpinned by the idea of conservation of momentum, and we'll have a look at how that is and what that is in order to explain that scenario. And as I said, there'll be a few other examples at the end where you can have a bit of a think about how conservation of momentum works in those cases. So if we think about what happens with a rocket, there is some sort of rocket fuel that is ignited, and in the ignition of that fuel it causes exhaust gases. Causes exhaust gases to be expelled from exhaust nozzles. So if we look at a bit of a diagram of what I'm talking about there, so we've got these exhaust nozzles on a rocket that are fairly long, fairly large. They're usually somewhat tapered because they need to expel the gas, and usually it'll mean that there's a fairly narrow opening that then expands. So they would be on the bottom of the rocket. The rocket then has a bit of a payload in there, whatever it is, and then it would continue to move. So in this case the rocket has a mass, we're going to call that mass M2. Without these exhaust nozzles, we have the exhaust gases being expelled, and they will have a total mass of M1. Now those exhaust gases will be moving with a velocity v1, and as a result the rocket then moves in the opposite direction with a velocity of v2. Now if you think about a rocket, usually we'll have a situation, say if we're thinking about a rocket taking off, the rocket will initially be stationary. If we're thinking about a rocket that's moving through space, then it might have an initial velocity. Ultimately though that initial momentum will be maintained. But if we look at this simple case first of a rocket that is initially stationary, the total system momentum will be equal to 0. Now, in order to get the rocket to accelerate, the exhaust gases are pushed out one way, so there's a force pushing those exhaust gases out, and as a result we, according to Newton's third law, will see a force that causes the rocket to then accelerate in the opposite direction. But the important thing to note there is that there are no external unbalanced forces acting on the system. Just making that note. So that means as the exhaust gases are expelled, they will have a momentum of the mass of the gas that's expelled, and let me just write the full equation here. So that will be the mass multiplied by the velocity, and so the momentum of the rocket will be given by P2, which is m2, sorry, I forgot one there, m2 times v, v2. But considering that the rocket was initially stationary, we can say that the initial momentum is equal to m1 v1 plus m2 v2. Or, more to the point, we can then say that the momentum of the rocket, so if we take m2 v2 over to the left-hand side, or let's actually express it in terms of m2 v2, so the momentum of the rocket will be equal and opposite to the momentum of the exhaust gases. So m2 v2 is equal to negative m1 v1. Now this negative here basically just means that they're in the opposite direction. So you can see that the exhaust gas is being expelled to the left in the diagram above, and the rocket starts to move to the right. Another point to note here, the rocket itself has a much larger mass than the exhaust gases. What that's going to mean, given that the two momentums are equal, then it means that the larger mass has to be balanced out by the velocities in order for the momentums to be equal. So the exhaust gases have a much higher velocity than the rocket. So in order to get the rocket to move at a fast speed or a fast velocity, the exhaust gases need to be expelled even faster than that, so significantly higher velocity. It's also worth noting here too that we're not actually looking at the what happens with the change in momentum with the rocket being initially stationary to moving. That's another discussion that we'll have relating to the next video. So we're ultimately just looking at what happens before and after. If you think about the exhaust gases, they're not all being expelled at the same time. They are expelled over a period of time. So there's actually a rate of change of momentum that's important to consider there, and we'll deal with that in the next video. A couple of other examples that you may wish to consider. I'll just make a note of these here. And we can have a discussion about these and how conservation of momentum applies in these scenarios. The first is the recoil of a gun. So when firing a gun, you'll often see in movies and TV shows that as the gun is shot, the bullet goes flying out the front and the gun sort of kicks back in the opposite direction. Another example is a fire hose. So with water being forcefully expelled from the end of the fire hose, not firehouse, the hose itself sort of recoils in the opposite direction. Or you can even think of a garden hose. If you turn a garden hose on without holding it, it'll sort of start to do that snaking around through the air kind of idea, and that's another example of conservation of momentum. And the last one to think about is a helicopter. So helicopter hovering or even lifting off, another example where conservation of momentum is important. So have a think about those three scenarios, see if you can identify how conservation of momentum applies in those three.